Yeah, so before I begin, just want to say today it might be my last time with you guys. Yeah, doing Atomistique. Even though I really wanted to go on, but uh, due to limited time, I was just given 3 weeks to teach you guys a lesson which is taught in about 3 months. So yeah, so that's why you see some topics I was cruising, some topics and some topics I was making sure I know the topics which I was making sure that you guys you understand. Yeah. So all in all, the most important thing for me is you have the base, and yeah, you have the base. You know something, like you know what you are expecting, which will give you actually the courage when you go to your various fields, your various schools. It will give you the courage of you facing anything, and of you actually becoming the best in chemistry. I want you to become the best in chemistry in such a way, like when you go to your various schools, chemistry actually is something which most of the Zabias, they, like, personally for me, I find it is something which is very easy. And if you just follow the rules, you just know how to calculate all those, you won't find any problem with chemistry. Yeah, and I would love that when you go to your universities, uh, the lowest must get 15. So your ranges must be between 15 and 20. Yeah, if uh, because I remember for me, like my mark was between 15 and 20. So if someone wants to pass me, has to get between 15 and 20. I won't tell you the exact mark, but yeah, so that's what you should do. So what you should do when you go to school, when you go to universities, just have a positive mind. Don't there's sometimes your seniors will tell you a lot of things. No, school is difficult. What? It's all about, like, you should know this. Your capabilities is not the same as their capabilities. So if they say it's difficult for them, for you it can be easy. So don't go with that mindset. Things are difficult. Nothing is really difficult. You just need your determination, your hard working, and don't like the only secret, don't leave work to be binding. Like if someone gives you work, if your professor at school gives you uh an exercise, make sure you do it. And most of the times they'll give you exercise for the topic. Like before they start the topic, they'll give you the exercise for almost each subject. So what you do is when you go, like there are some days where you go to answer those exercises with the professors. So what you should do is before you go to classes to answer the exercises, make sure that in each subject where you're going to answer the exercise, make sure you do just a bit or a part of exercises, so that when you go that side, you have a clear view on the things which you are doing. And participation, when you go to your various universities, participation is very important. If you participate, they will give you marks for participation. And you have to create that relationship with your prof in such a way that even though if you don't do well, the prof actually can make you to pass to validate your way. And you'll be surprised. Like sometimes you'd find the exam is very hard, or the like for us who have controls, like you find the control is very hard, and uh, you even lose hope of passing. But because of the prof liking you, because you participate in class, because you are always active in class, he'll give you a mark definitely. That's what usually happened. He'll give you a mark. I remember I had a control in chemistry. Actually, I missed the control, like the midterm test was like a control. I missed the control. I was late, and because of the relationship which I had with the prof, I asked him to write the control the other day. He made another test for me. I went to go and write in his office actually alone. I wrote it, and that test, he added something which he said at first won't add, and I was disturbed in chemistry. I was disturbed. Like I didn't study those things. I only studied the other part. So it was something else. But because the relationship which I created with the prof, I found out that when we had our exam was very simple. Like if I didn't get everything, then I don't know. But our exam was very simple in such a way that when my mark came, my final mark, the control and the final exam, when they added it together, it was between 15 and 20. So what you should do, one, you should never lose hope when things come back. Just work hard so that you hammer the final, those who will be having controls. And two, just have determination. You always make it in life, determination, and have a positive thinking. No, analysis is hard. Analysis is not hard. Algebra is not hard. Nothing is hard. It's just your thinking, your positivity, and it all starts from your positivity, how you think. That's where everything starts from. So to make it, you have to be hardworking, observe time also, and also work in a group. Those who be going to their universities, try to work in a group so that when you work in a group, like with your friends, maybe if you be with Zambians, you work with Zambians, and maybe with Moroccans also, especially Moroccan girls, like they are very serious. For boys, they're not serious. Like Moroccan girls are very serious. So you work with those people, like don't isolate yourself, because you'll find that the Moroccan girls or the Moroccans themselves, generally they'll help you sometimes, yes, like that. So be open-minded, don't be scared of anyone, don't be scared of any subject, and you'll make it. You'll be able to validate all your modules, all your subjects. Yeah, because it's not possible. People have done it and I've seen it, and yeah, and validating, I've seen that validating is not something which is difficult. Like if you put determination, you validate. And we want you to be going forward, not you remaining. So want everyone to be going forward. When you go that side as Zambians, don't compete, work together so that you see each and everyone to go forward. Because if you pass and your friend who you are sleeping with fails, it's something which is very bad actually, because you can't even be happy. Like for example, you validate all your subjects, then your friend who you are with doesn't validate anything, or validates only two. It's something you won't even be happy. So make sure that if you are living with a person, make sure you work together and you validate together and you enjoy life together. Yeah, because like for me, I'm living with my friend, and we always like, if I validate all the subjects, I know that he has also validated all the subjects. So that's it, because we work together. He's in another class. If I don't understand on a subject, we do the same subject. I will tell him, no, when you go for class, you should listen on this part, and you should come and teach me. So that's basically how we do it. So yeah, so with those few words, we're going to start with our learning today. And I would want us on Sunday to create a day. I know in respect of those who will be going to church on Sunday. So afternoon, I think is okay, where we can create a day. And I'll explain to you I want to explain to you the last part about the questions which I gave you. Slaughter, those things, I just want to touch there so that you guys have an idea, especially the electron configuration, which is very important. You have to know it. Yeah, so on Sunday, I'll communicate to you in the group, like the time and everything. And on Sunday, yeah, you should be there so that we do these things together. So without wasting much of your time, we're going to start with our lesson. Can you see my sharing?
Yes.
So we're going to start with our lesson. So just a quick recap. Last time we looked at nature on the electron, the electron. So the wave-like nature of an electron. That's what we looked at, and we discovered that an electron actually it has a wave nature and a particle nature. That's what we discovered. last time when we were learning about these things. And we also discovered that it was impossible, since we have said that this electron was in the form of a wave, it was impossible for us to know its position and its movement on the same time. It was impossible. It's either you know one, you don't know the other, or it's either you know one and you don't know the other. So that's the thing which we did. We also did the principle of incertitude of Heisenberg, where Heisenberg he said basically the same thing, that the position and the quantity of movement cannot be known simultaneously. It's either you know one, and if you know one, you can be able to calculate the other. You can't know them at the same time. So here there was a variation of quantity de mouvement. After differentiating this one, then after that, this is the most equation under incertitude. This is the equation which you should do basically pay attention on. And I think I'll give you the last exercise on under this under this topic, and it will come on incertitude of Heisenberg. So when I give you the exercise, you should just come on this incertitude of Heisenberg and you see the formula and you try solving it. So the most important thing is you must know how to calculate. So after that, so after that we moved on and we associated this particle with a function don't. A function don't is a wave function actually. So a wave function like is represented in psi. You say psi, psi. It depends how you pronounce it. It's PSI. So that's how we represent. That's how we said it should be represented. Where the wave function is the probability of finding an electron. The probability of finding an electron around a nucleus, like you can't find, we said an electron, we said like we discovered that you can't really know its position. It's like the position is what changing. So the wave function is, they came up with something like a wave, and they said for us to find an electron on this wave, we can't really know where an electron is in this wave. We just come up with a probability, like we just say, okay, it's like either it's here, either it's there. It's just like I can say a probability. So we see that here under function don't, we see that an electron, what you should know is function don't, it's a wave function which tells us that you can't find an electron you can't know its position, but you can only know its probability, since we have said that an electron has a wave-like nature, and it's very difficult to know where a wave is. Basically, it's very difficult. So from there, the same things under wave function, all that. So those things. So the basic thing here, what I just want you to know is, this thing is actually something which is just a base, and something which will lead us to see an electron in a three dimension. Like it will lead us to see an electron in a 3 dimension when we discover, when we learn more about this thing. So what I just want you to know here is, one, according to Schrödinger and Bohr, it was, for them, they discovered that an electron is a wave-like, has a wave-like nature, and its position is very difficult to know its position and what on the same time. So that's basically what you should know. So we moved on, we looked at all those things, and also looked at conditions are remplis par le function done. So what condition must be fulfilled by function done? So we say that la somme de probabilité étendue à un volume infini est 1. So it means that when the sum of this probability, when we add all these sums of probability, they must give us 100% in such a way that 100% is just the same as 1. Like it must give us a whole. If we have infinite of these probabilities of finding an electron, and we add these probabilities together, it should give us it should give us a sum of probability which is equals to what? To 1. So basically, that's it. And the second part was the function don't, or the wave function doit être régulier. So we said that this wave function must be regular in such a way that it must be what? Progressing what? It must be progressing. It must be in a regular progress. Like when it's moving, there must be no discontinuity. Like when it's moving, it must be what? In a regular what? Yeah, when you see here in a regular progression, not it has moved, it has reached here, then it stops, then here, like for example, we see like it makes something like a HN, then it stops, then after that, it starts again moving. No, that's not the way the function don't is. The function don't is when you when you are finding the probability of this electron must be moving in a wave-like form, which is in a continuous form, which is progressing and which is what? Regularly. Which is what? Which is regularly. So, yeah, so that's what you should do. No, and you should also know that psi or function don't, this is the function don't, or the wave function must be uniform. Uniform in such a way that if I find the value, for example, if psi or psi is found here, it must correspond where I found it. I find it on another wave here. Since we said you can't find an electron, it's a you can't find on read the position of an electron. You can either find it if it's here or here. Like if an electron is here, basically it must correspond on the same, like if you see here, it must correspond. It must be in a uniform form, such a way that it is corresponding. And that's why here I said if you have CT must be equal to CT, we say psi t must be equal to psi t apostrophe, meaning they must be found even though they are on different height, but the position, exactly position must be the same with this electron. You can find it, for example, if it is on +2, your x, if your like for example, let's say your x is 1, like you move from 0 to 1, then your y must be +2 and -2, meaning you can find it on 2 the positive side and on -2 the negative side. That's the rules which the function don't must follow, and the function don't must be fini on tout point. So also say that this function don't, if I draw my wave and the wave is finishing here, it must finish on the same level, like it must be finishing all the points. So yeah, so basically those are the rules which the function don't, or the whole function has to follow. So these things, like after we discussed, like last time when we met, we discussed about all these things, like we talked about all these things, and we came up with how these men Schrödinger and Bohr had in view of an electron. So we see each man from Rutherford, from Bohr, and the Bohr and Schrödinger had a different view of how you can view an electron, how an electron is moving around a nucleus. So each of them had a different view, and each of them had, like, as knowledge increased, they also increase in how they explain these things. So we see Rutherford in his time, he never had that much knowledge. Then we see Bohr on his time, he never had that knowledge in such a way that there are no maybe experiments or what. And we see in Schrödinger and Bohr had that. It's not that much knowledge, or it's not. They don't have much equipment, but they had equipment more than Bohr, which made them able to find out that actually an electron, it behaves like a wave, like light, and it's difficult for us to know its position. And you should always know that this function is independent of time in such a way that it doesn't depend time, as we discussed earlier. When it's moving, it doesn't depend time. When an electron is moving, it doesn't depend time. This is because when this wave is formed, this wave forms like a circle, like meaning, as I described here, when an electron is moving, assume an electron is moving in a what? In a wave form. So when it is moving in a wave form, it creates like a circle-like thing. So that's how it's moving, and it will go back to its initial. So meaning this thing is basically like it's independent of time in such a way that when it's moving, it always goes back to what? To its what? T initial, and meaning that the final results always will be giving you the T initial when an electron is moving around a nucleus in a waveform. So it's independent of T. So today basically we're going to look at the equation of Schrödinger. So this equation of Schrödinger is not something which is very difficult. The equation of Schrödinger actually is not something which is very difficult. So before I start with this equation of Schrödinger, so Schrödinger, this man like Schrödinger is, he wanted really to know the position of an electron, since you said it's impossible to know the position of this electron, and he wanted to find a way of calculating the total energy of this electron, seeing that he has discovered that this electron is a wave. So in doing this, in calculating this, he had to put something in mind. Yeah, he had to put something in mind to calculate its energy. So here, under equation of Schrödinger, actually is dealing with how can you calculate the energy of this wave. Like, it's very difficult to calculate an energy of something which is moving in a wave. So he wanted to come up with a formula, an equation of calculating energy of an electron which is moving in a what? In a wave form. So how did he do it? So I'll give one example. Yeah, I'll give one example. I hope this person doesn't mind. I'll give an example of Musonda Chanda. I hope Musonda Chanda, you are there. Since yesterday it was your birthday, so in honor of your birthday, I'll give an example. Yeah, so Musonda Chanda, I'll give an example of Musonda Chanda. So if, for example, let's assume he's at home and he's at home and he's with his parents at home, and what happens is he was at first he was in the sitting room with his parents. Then he tells his parents, Dad, Mom, I want to go and study. Then he goes to his room. So when he goes to his room, you see that in his room there's a bed, there's a studying table, and in his room, his parents actually bought him gaming like PlayStations, Xbox. Let me say Xbox. They bought him an Xbox. He has a TV in his room. So what happens is when he enters in his room, you see that when he closes his door, there's his parents, like according to the way they know him, his parents, they have got 80% probability of thinking that Musonda Chanda is playing games. Then they have got I can say they have got 80% probability of Musonda Chanda playing games. They have got let me say they have got 70%. Yeah, they have got 70% of probability that Musonda Chanda is playing games, and they have got they've got 20% of probability of him sleeping and 10% of probability of him studying. So for them to know what actually happens is they have to open the door and check to see what Sondachanda is actually doing. So we see that probability, like Schrödinger put in mind of a probability. Since an electron, we can't know its position. We don't really know its probability of where it is, and how can I find the energy of something which I don't know the probability? Can be either doing this thing, can be either in this position or in that position or moving in. So that was the probability which Schrödinger had to put in mind in calculating energy. So in the equation of Schrödinger, you'll find that he'll put in mind some probabilities, or he'll bring something which shows a probability of him when it comes to calculating. You can also give an example of the famous experiment which he did, like the one for Schrödinger's cat. I think you heard about it. Schrödinger's cat, actually, he took his cat, he put it in the box, and he got a radioactive element, and he put it also in the box, and he closed the box. And that radioactive element could kill the cat. Yeah, it had power to kill the cat. So for him to know that the cat has died or not, he only had the probability. He can't really know if the cat is alive or if the cat has died. Like, it was difficult for him to know unless he opened the door. So like when the box is closed, you only had the probability if the cat is alive or dead. But when he opens the box and sees for himself, that's when he'll be sure that the electron actually is what is or the cat, the cat actually is dead. So when he hasn't opened the box, there's two probabilities. It's either the cat is alive or the cat is dead. So that's according to this experiment of the cat. So putting that in mind, Schrödinger wanted to find a way of how can I find energy, and how can I find the position of this electron? Like, if I open up the box, how can I open up the box and I see what is inside and I see its position? Since me and my friend Brogy, we have discovered that it's a wave and it's difficult to actually find this position. So this is how the equation came about. Yeah, so we see that this is how the equation came about. So we'll start with the equation of Schrödinger. It starts: il ne suffit pas d'admettre l'existence d'une onde associée à une particule, mais il faut la déterminer. So it is not sufficient to admit the existence of a wave. Like we said that there's a wave and of a particular, it's not sufficient to only say that this electron is moving in a wave, but we should determine it. We should know where exactly this electron is. Since we have found out that it is a wave, how can you be able to find this position? So we see en 1926, c'est Schrödinger qui formulait la première équation différentielle de la fonction d'onde. So we see that Schrödinger is the first man who first formulated an equation, a differential equation of wave function, or of the function d'onde C or psi. So the equation de Schrödinger independent de temps, ou in particular the mass M, the energy potential V, c'est écrit. So we see that this equation of Schrödinger's, it was independent of time, since we see that an electron is moving in a wave-like form, and when it moves from T initial, it goes to T final, then it goes back to T initial. So he said it's independent of what? Time, for particle of mass M and of energy V. So when he had put this in mind, introducing also a function d'onde, A function don't, as I said there, don't be confused of when you see psi, what, don't be confused. What does this really mean? Like, why, how can you even calculate this? Like, this simply simple. This psi simply means, the psi, it simply means the position where you can find an electron. So since it is a wave, it's a wave function. So we have to introduce a wave. So this is the wave function where you can find an electron. So actually, I want uh, uh, to highlight something. So for example, if just check this wave, like where the arrow is going. Yeah, just want to explain something. Just check this wave. So what usually happens is, when an electron is here, like when an electron is on the crest, yeah, we say a crest. When an electron is on the crest, there's high probability of, its probability of finding it is very high. Unlike when an electron is here, where the wave is cutting with the x-axis, where the x-axis is 0, the probability is like, yeah, I don't know if you can get me.
Yes, yes, we can get you.
Okay, so the probability of finding an electron here is very high. Then the probability of finding an electron here, because it's cutting here, x is equal to 0, and the probability actually is 0. Then here, where where the wave is going down, the probability also is high. That's why, so you can find the probability here is high, like uh, when an electron is here is high, and when an electron here is high, the probability is generally, there's no probability when it's cutting within the x-axis. That's what you should know. So yeah, so that's the function. Like when you talk about the function generally, the function don't. Yeah, so this function don't is just the probability of where you can find an electron. And the many of the physicians for over 100 years, they have tried to crack this formula, and they have tried to explain this formula. Each person explains it in his own way, and actually no one can really come up with a good explanation on this formula. And that's why most of the times you'll see that this formula, actually they don't even use it, like they don't use it in calculation, because the owner, even him, Schrödinger, who formulated this formula, he couldn't know how to use it in such a way that after he formulated this formula, he was confused by it. And when he was confused by it, he had to leave this formula and start some research in biology. Like he had to quit physics, I can say, because the same formula, this formula himself, it confused him. It was not until Max, I've forgotten the last name, but Max, a certain scientist, who came in and explained it more, and he gave us something like to know about this formula. Yeah, so this formula is actually the backbone of mechanical quartic. It's a backbone where mechanical quartic is actually when you talk about the Rendueta, the what, like, yeah, when actually the mechanical quartic is simply talks about the wave-like and the wave-like wave-like nature, and the particle-like nature of an electron. So under mechanical quartic, this equation was the backbone, is very important. And this equation, when Marx had to prove it, when Marx had to explain more about this equation, actually they found out that they used this equation, the laptops which you are using, you've seen that you have got some chips, and some chips that have got some electrons, something like malines. So if you have seen some chips of a computer, of a laptop, actually it came out from this equation. So for you, it's possible to see something or to see yourself on a laptop or what because of these things. So this was actually an equation which is a backbone, and like people really can't really know how to explain it. So the equation is basically simple. This is the wave function, which I've said the probability of finding an electron. Then don't get confused with this one. This one simply is V. We've already talked about V. V we said is potential energy. If you remember back from Bohr, we said V is potential energy. So if V is potential energy, this other one is what? Kinetic energy. So here is just potential energy plus kinetic energy times here they just consider the what? The wave for us to calculate energy, which gives us energy total of the wave. So they're just calculating energy. So this is the formula which they use to calculate energy, to calculate the total energy when an electron is moving in a wave-like form. And we see that the differentiation, differentiation, after you differentiate something, this differentiation sign or differential sign is simply is equals to d2 over d2 over x plus d2 over d2y plus d2 over d2z. Yeah, that is equal to that thing. That thing is like it's just the differential of the under x-axis, under z-axis, under y-axis. So don't get confused of that. For example, if I give you x squared plus y squared plus z squared, you know how to differentiate x squared. You know dx of x squared is just 2 minus 1 times 2. It will give you 2x. This is the differential. Then if I differentiate it further, that's why you're saying d2f over dx2. Yeah, so if I differentiate it further, you see that 2x will just become 2. So this is something which is basically simple. So that's what represent that thing. And there's no need of you like or memorizing it. I can tell you, like, even when you go to universities, even teachers, professors, like we had the situations where you have a TD in this one, a professor he just comes and gives you answers. Like, he can't really prove how to do it, and most of the times they don't usually, like, they give you they can't give you a test on this one. Yeah, in most of universities they can't give you a test in this one. And guys from mostly guys from BCG are the ones who go in details in this thing, like the calculating the what. But for guys in ENSA, MIP, and these other fields, SVT, they don't really go in detail. They'll just give you the formula here. H function don't is equal to E function don't. Then they say this formula is because of this and this. They don't usually explain it that much for ENSA and ENSAM guys. So yeah. So now we have said that E is the energy total. This E is the energy total. Then psi is the fonction don't décriver le mouvement de l'électron. This is the function don't which describe the movement of electrons. This was said is an electron is moving in a wave-like. So it describes a movement of an electron in a wave-like. So this is psi. Then this equation can be written in H psi is equal to E psi. So H just represents the whole part, this whole part, this whole part, this whole part. That's what the H represents. So the H is simply a a Hamiltonian due system. So Hamiltonian due system, don't be surprised with this big name. What does it mean? So Hamiltonian system is just it just describes the what. Since we said there was potential energy and kinetic energy, so it is an operator which puts the potential energy and the kinetic energy together. The calculation of the potential energy and the kinetic energy together, like they are put in the H. If you see V represent the potential energy, then this represents the kinetic energy. So when you see the word Hamiltonian, don't really get confused by it. It's nothing new, it's nothing special. It's just an operator which the physicians long ago, they said, since this one is a bit complicated, we'll just replace it by H, which we'll call it. And actually, this is just a surname of the one who introduced the H. Yeah, his name was, his surname was Hamiltonian. So yeah, if you want to have more knowledge on these things, you can Google, you check about this man, and you see, yeah, all that. So we see that in a nutshell, we see that cette équation de Schrödinger est considérée comme le principe fondamental de la mécanique quantique. So we see that this equation of Schrödinger is considered as the principle, the fundamental principle of mechanique quantique. And you said mechanique quantique, don't get confused with the name. Mechanique quantique simply the study of how an electron is moving in a wave like what form. So then don't get confused, just talks about the ondulatoire and the particle nature of an electron. So when they say mécanique quantique, just have that in mind. So la résolution de l'équation de Schrödinger est un problème mathématique relativement complex. And yeah, so it says the resolution of the equation of Schrödinger, it is a problem which is mathematically complex. Even him, the man who discovered it, couldn't even understand it, like Schrödinger himself. He couldn't understand it. And as I talked earlier, he abandoned it because it wasn't making sense for him. Like for him himself, when he was discovering this formula, he saw that it couldn't make sense for him. So he just abandoned it. Then, cette résolution montre que celle-ci n'a des solutions physiquement acceptables, ça est que pour certaines valeurs de l'energie. So we see that this resolution shows that we see that this resolution of the Schrödinger's equation, it shows that it only has it can only give answers for only determined atoms. Like it cannot be used for all the atoms. It's capable to give answers for other atoms. Yeah, mostly it's used hydrogen. Since it's hydrogen has one electron, you can use it. But these atoms, like which have a lot of electrons, which have a lot of energy shells, it's very difficult for you to use this Schrödinger's equation. Ces values particulières de l'énergie sont appelées values propres de l'énergie. So these values of energy which you find using the Schrödinger's equation, they are called the proper values of energy. No, I meant the values which I meant the values which you can not find by Schrödinger. I meant the values which the equation of Schrödinger is incapable of finding. They are called values proper of energy in such a way that you use, there's a formula like you find, and if those who did stratas, like if you did your research on stratas, approximation de strata, when you do your research, you find that there you calculate the energy for an atom which has a lot of electron shells, which has a lot of electrons, basically. So those, they give you the values proper of energy, and the function don't correspond to the function proper. Yeah, so the function don't correspondent. This one basically is talking about it's basically talking about this wave function is only correspondent to function which are proper. How can I say it? Something which is easy to calculate. I can say something which is easy to calculate. If something is difficult to calculate, to calculate, you can't find this. You can't find this function proper. You can't use the Schrödinger's equation, and yeah, and basically you can't really tell where you can't, if something is complex, you can't really tell this function proper. Yeah, but its energy you can calculate, even though some they can't give you the energy, the energy proper, but you see that for those under Schrödinger's, they can clarity, they can give you an energy proper, and they can give you a function proper. Then after that, I don't know if you are clear until there. Is there any question?
No.
Oh, okay. So if there's no question, we'll continue with it. So yeah, so that's all. That's basically about it. The application, the Schrödinger's equation. So when you continue, we see that this equation just written as H psi is equal to NH psi, and H we have said is Hamiltonian, the system, which is we have already, which is the just a combination of kinetic and the potential energy. Then we know, so yeah, we have already talked about H. Then V, we said this is the potential energy, which is when we did our calculation back then under Bohr, we found that this was our formula, negative E squared divided by 4 pi epsilon r, where negative E squared is the charge, 4 pi epsilon r is the radius. So we discussed about this one already. Then
Excuse me.
You have a question?
About the Hamiltonian. Yes. This one H of which you said is Hamiltonian. Does it mean that it has a constant value that is already given? Is there a constant value we have to know of this H, which is Hamiltonian?
For H, I can say, but I haven't seen like where they're saying there's a constant value, but it's always, most of the times it's always calculated like it's something which is very complex. You can't really calculate it, like something very complex. So it has to have a constant value. Yeah, that's what I can say.
Okay, thank you.
So, pour résoudre cette équation, on choisit le coordonnant sphérique R, pi, and there's R. This is pi, and this is what do you call this word? Yeah. So there's R, pi, and theta. Okay. Yeah. There's R, theta, and I've just forgotten the name of this symbol. Yeah. But they are represented in this like in a form of what? In a form of strict form. So there's R, pi, and this other symbol. Yeah. So how can you, so according when Schrödinger discovered, when Schrödinger when Schrödinger discovered the equation, when he discovered this equation, actually in his equation, when he solved this equation, it gave him that this electron, when it is moving, it's moving in a what? Spherical form. Just imagine if, and if you imagine according to Bohr, I said that the orbitals were in a circle form. If something is in a circle form, meaning it will give us something flat, and if it gives us something flat, it will be for example, if our Earth is flat, meaning we can't have this space of building things, we can't have any space. So according to the equation, when he solved this equation, when Marx actually proved this equation, it was found that the Earth actually was in a form of a spherical form, in such a way that when it's in a form of spherical form, it is represented in a kind of 3 dimension, which when you see here, I think those who do, for those under BCG, you never did this, but for those answer, you have done what? Under mechanic du poids, you have done coordinates on a spherical form. Yeah, coordinates of a sphere, you have done that. So, for example, if an electron is here, it's possible to see its position here and to see its position here, which creates a 3 dimension in a form of what? Spherical form. So after solving this equation, he found that it was found in a what? In a spherical form. Yeah, in a spherical form. So we see that this is what? This is pi. This is psi, and these are angles which are formed here. These are angles which are formed here. If you see the angles which are formed here, yeah. So we see that imagine an electron is here, and this is a radius which you form from the center, from your center to here. This is a radius. Then you have to bring, like you have to bring a line at a 90 degrees down, where must be the same position of I, must give you the same position of I must be the same here. Since my drawing is not in scale, that's what I've seen. M and I, they're not on the same one. They're not on the same position. Yeah, they're not on the same position. So we see that the same position, the position of an electron here must be on the same position here. And you draw a line which will join here, and this line will make an angle of psi. So this is the probability. Basically, this one is showing us that an electron can be found on something like it can be found in a 3D, like you see it on I, you see it on M, you see it on N, like you can't really, its position, like it's something which is, for you to really know its position, you have to unveil it in such a way that you have to know your I, you have to know your M, you have to know your N. So if you know your N, you know your M, you know your I, you can now find the position of an electron. So that's how when you solve this equation, those are the coordinates which he had, and those are the coordinates which he found, and the coordinates showed him that actually this electron is moving in a what? In a spherical form, and when it's moving in a spherical form, it's able, if I know my N, I will know my M, and I will know my I. And these MI and MI, they are called quantic numbers, and we are going to look, these are the things which we are going to look more on them, and we're going to discuss more on them, and you'll be able to know what they really represent and what they really mean. So these signs, this one and this one, they just represent the angles. They just represent the angles, and the R just represent the radius. So don't get confused. Yeah, don't get confused. So it's something which is basically simple. So the function, don't is sous forme d'un produit d'une partie radiale R. So we see that this function dot is a form of in form of a product, or a product which is R. So we see the R, since you know that R is radius, and the radius basically it tells us the position. So this R is in changing, so it gives us the probability. The R, if you see the R, if you know where the R is, it gives you the probability. And the d'une part angular is just the angular part, the angle part, which this radius makes with the Z, the Z, which is this angle here, and where this M makes with the X, which is this angle here. This there, the angle which makes when an electron is, like when you are trying to determine its position. So we see the equation de Schrödinger now the solution pour certain values there in. So we see that this equation of Schrödinger has only solution for some values of energy. So energy 1, energy 2, energy n. So yeah, so it only it cannot be calculated like for, as I said earlier, for atoms with a lot of electrons. It's possible. It's impossible to calculate, but for electrons of I can give hydrogen, whereas 1 electron is it's possible to calculate. And this energy, when you calculate this energy of the shell, is usually what quantified, like as we discussed in Bohr, like the energy is fixed. And when you see this when you see this formula here, it tells us that this is the same formula of Bohr, in such a way that here they're just replaced by negative 13.6 here. You just replace this one. So just the same with Bohr. So avec n et le nombre quantique principal, on trouve donc pour l'expression donnée dans la théorème de Bohr. So we see that if n is a number quantique, or this is the n which is number quantique, we see that, as I explained there, we see a theory which was, or a formula which was formulated by Bohr, which is this formula. And la recherche des solutions R and the angular, the part angular of these two signs will show 3 number quantique n. So we show 3 number quantique n, I, and m. That's what it will show. So we see that when you search for the solution of this one, the solution for this electron, we will come up with 3 number quantique, which will look in more details. Which this number quantique, it will give us the 3 dimension of an electron, and you see that when you come to learn it more, you basically understand it. Yeah, you understand it clearly, and you'll be able to know what really we are talking about. Yeah. So we see that if we know our number quantique n, I, and m, if we know our number quantique n, I, and m, it's possible for our solution to be acceptable, because if we know first we know our principal quantique, which is n, our principal secondaire L. You learn. I'll tell you more about it. And this m will present our magnetic number. Yeah, so we'll learn more about it. You'll be able to actually find the position, and you'll be able to find some solution which are acceptable if you use this formula. So you see that psi is equal to NIM. This is the position where you can find an electron, which is open bracket, the radius, and the 2 angles where you can find this electron. So these are these signs. They present what? These signs, they present the 2 angles when an electron is moving. So basically, so on these signs you can this is an angle sign. Then if you want, you can press any sign, but if you should just know that these signs, they represent they present what they present the angles. Yeah. So they try to use just different signs so that you can differentiate the angles, showing that the angles are different. So there's nothing special about it. The same things, the angle signs. So you see that R and I. So you see that R, our radius is under the line of Ni. Because this one from 0 to I, it gives you radius, part of radius of an electron, and from 0 to N, it gives you part of the radius. Then you also see that Im is the one which gives you the angle. We see that Im, so the R makes an angle with the Z, then the M, it makes an angle with the X. So basically here, what you should know just is, they create something like a 3-dimension, and they create something like a spheric, and this electron is moving in a spheric, and if this electron is moving in a spheric, it correctly explains why the Earth is in a spheric form, and why the Earth, we can be able to move about in the Earth, we can be able to build higher buildings, we can be able to do all these because of their discovery that these electrons actually moves in a spherical form. So that's all which you should know. And we're going to open up, and we're going to see more of what N means, what M means, and what I or L means. Yeah, I don't know if it's clear until there. There's any question you can ask? Okay. So yeah, so this is simply like after getting all that, after coming up with the base. So here, like I was explaining this thing so that we can come up with the base and know how to explain these quantic numbers, which is M, N, and L, how we can explain it and how we can explain them. So now I'm going to explain them in a more simpler way, in like the stages which we can go, since Schrödinger helped us to find that actually an electron it moves in a sphere, and to find its direct position, you have to know its N, you have to know its M, and you have to know its L. So for me, to find this direct position, I have to know all those things. So how do I do it? So this gives this, now we're going to, nombre quantique. So we've discovered that nombre quantique, we've discovered 3 nombre quantique, which is N, L, and M. Those are the 3 nombre quantique which we've discovered. And now, how do we explain them? How, what stages are we going to move for us to actually find where the electron is, where an electron is? So, what happened was that after that discovery, we see that Sommerfeld came in. So we see that, so under nombre quantique, pour interpréter le spectre de plus complexe que le hydrogène, Sommerfeld utilisait des trajectoires elliptiques. So Sommerfeld, using the formula of Schrödinger of an electron having quantic numbers M, L, and N, and also using the formula of Bohr, seeing that these electrons, they move in a shell, but for him, he added that these shells actually, the shells, yes? You can ask? Is that a question or? I think he's talking on the phone or what?
Yeah, it was on phone, but you can continue.
Oh, okay, so number quantic. So Sommerfeld, he got the idea of Schrödinger. So we see Sommerfeld under number quantic, he got the idea of Schrödinger, in which he said actually the electron moves in a shell which is in a form of what? In a form of elliptical. Elliptical meaning like you know how an egg is. You know how an egg is. That's how he discovered when he solved this equation when he was finding the position Schrödinger, the Sommerfeld, and he also used the idea of the same idea of a shell for Bohr. So Sommerfeld. He was just making better the formulas which had already been found by Schrödinger and Bohr. So Sommerfeld was just making things for them better, for both of them better. So yeah, so one, the electrons were moving in a what? In an elliptical form, which is a form of a shell, and also using the formula of what Bohr discovered. He said that there are shells, and these shells, they are represented by nombre quantique n. So that's what we are going to starting right now. So when I'm talking about these things, I want you to put this in mind. When I'm talking about these things, the nombre quantique principal n, the nombre quantique secondaire, the nombre quantique magnitude, and the spin, which is the fourth one. When I'm talking about this, just imagine there's an apartment. Yeah, I can say a flat. I can say a flat. Yeah, an apartment, a flat. Just imagine a flat, and a flat, it has got different stages, and each stages has got some apartment, and each apartment has got rooms, and each room is occupied by people. So when I'm explaining it, I will start from the apartment itself. Then when I explain from the apartment side, this is how we are going to discover where an electron is really. So I'm going to start from the apartment itself. When I talk about the apartment, I'll go to the stages. When I go to the stages, now I'll go to the the apartments. When I go to the apartments, then we'll look into the rooms now. And when we look into the rooms, we'll find our electrons there. So it's something which is we're uncovering something, like we want to see really where we can find an electron. So the first one is nombre quantique principal n, which is an apartment. So this one is nombre quantique principal n. As we discussed in Bohr, we said that nombre quantique principal n is it represents the shells. So when I say nombre quantique principal n, I just mean the shells. So this electron is moving in a shell, which is an apartment. It's moving in an apartment. Yeah, it's not outside, but it's inside a shell. So it's moving inside the what? A shell, an apartment. And we say that n must have the values of 1, 2, 3, 4, like the first shell, the second shell, the third shell, the fourth shell. Yeah, remember these niveau K, niveau L, niveau M, those things. Yeah. Then this about the circles, don't get confused. I was just trying to, I couldn't find the really good diagram, but I was just trying to show you guys that you can, like, for him it was in a spherical form, so don't get confused. Like, I was trying to show you that now they consider that this electron is moving in a spherical form, which gives an atom a shape, which gives an atom a shape. Yeah, so number quantique principal M, I said this is an apartment in which an electron is moving inside, and this is represented by 1, 2, the value is 1, 2, 3, where n is equal to 1, niveau K meaning the first shell, n is equal to 2, niveau L means the second shell, n is equal to 3, niveau M, which means the third shell. So we have talked about the apartment, which is the principal, the nombre quantique principal n. So after talking about the apartment, now we're going to talk about the stages, like the first apartment. When I've talked about the building, actually, the flat, the flat, not the apartment. When we're talking about the flat, we've talked about the flat is moving inside the flat. Yeah. Then now we're going to talk about the stages, like where you find the apartment. The stage 1, stage 2, stage 3, stage 4. So now we're going to talk about a stage. So this stage is represented by nombre quantique secondary L. So after we have known that it's moving in a flat, and want to really identify its stage, and wants to really identify its apartment, and after that we want to identify its room. So now we're at the stage side. So how do you know that this electron is found on, how do you know its stage? So the stage is known by the nombre quantique secondary L. So keep on the value the 0 n minus 1. So we see that the nombre quantique secondary L takes the values of from 0 to n minus 1. So this electron is moving in a shell, and for me to find its subshell, we can say the stage is just the same as subshell. So it's a shell. Now we're looking at the subshell. So for me to find its subshell, I must subtract the niveau where I am, or the level of the shell where I am. If for example I am in shell 1, for me to find its subshell, I must subtract by what? 1, which means L is equal to what? 0. When L is equal to 0, it just corresponds to the what? To the first shell, and it just tells me that I can only find this electron, or this electron is found in the what? First shell. So which is L is equal to what? To 0. Then if n is equal to 2, you have n is equal to 2. When you have n is equal to 2, since you said you start from 0, so you start L is equal to 0, then you do 2 minus 1, it will give you L is equal to what? To 1. So you start from L is equal to 0, then 2 minus 1, L is equal to 1. So here it shows us that in the what? In the second energy level, or in the shell energy level, I can find it. This electron, I can find it at L is equal to 0, which is denoted by which is just the same as it's denoted by S most of the times. Yeah, I can find it at L is equal to 0, or L is equal to 1, which is denoted by L is equal to 0, always denoted by S. So when I go to 2, I can either find it in this, when energy level is 2, it becomes a bit complex, because I can either find it in the shell where L is equal to 0, or I can find it in L is equal to 1. That's how. So when you go, when the number of shell increases, it becomes more complex. So that's how we go about it. So the stage part, that's the stage part. I can say the what? The sub what? The sub shell. And basically this what gives an atom actual size according to its nombre quantique secondary. It gives the size of an atom actually. If you want to know the size of an atom, you have to know the is nombre quantique secondaire. So if it's, for example, for N1, you know that N1 is nombre quantique secondaire is L is equal to 0, meaning basically it will be smaller than N2, which nombre quantique secondaire is L is equal to 0 and L is equal to 1, meaning it has added one nombre quantique secondaire, meaning it's something which is big, and if something is big, it becomes a bit complex for you to find the actual position of an electron. So we shall see that L is equal to 0, it corresponds to the subcush. Subcush means subcush S. So L is equal to 0, it corresponds to the subcush S. This one you will understand more when you come to calculating. Those who did the questions which I sent you, the assignment which I sent you, I think you saw something like S, the P, the D, the F. Yeah, those things you understand them more when we come to learn about electron configuration. So L is equal to 0, it corresponds to S. Then L is equal to 1, it corresponds to what? To P. L is equal to 2, it corresponds to D. Then L is equal to 3, it corresponds to F. So these are different sub-shells. Sub-shells meaning if L is equal to 0, for example, N1, I've got L is equal to 0, meaning if I'm writing my configuration, I'll only have a subpush S. So it will be 1S to the power 1. That's the subpush which I'll have. But if I have N is equal to 2, meaning I'll have the first subpush, because I have L is equal to 0, and the second subpush, which determines the size. So you find that the first subpush or the first subshell is 1S to the power 2. Then you go to 2S because of L0, which represents S, 2S to the power 2, and 2P, for example, to the power 1. So those are the electron configuration when you come to writing an electron configuration. These are things which you learn. So yeah, so basically it's something which you already know, even though in Zambia we were doing the electron configuration, which was a bit different, where you could start from 2, 8, then you go to 18, what. But for here, they present them in a form of S, P, D, and F. That's how you write the electron configuration here in Morocco. You don't just write directly. When they tell you write the electron configuration, you just start writing 1s squared. You just start writing 2, 8, what. They don't write like that. Like they don't write directly. You have to know that N1, if my N is equal to 1, or if for example, if my atomic number is equal to 18, I have to know how to write an electron configuration. If my atomic number is equal to 4, I have to know how to write an electron configuration. So this is this. So the first part, you have the flat where there's a shell. Then after the flat, you go to the subshell where there's likely you can find, this is where likely you can find what? The electrons. And these subshells, they are different. They tell the size of actually, and the size of it tells the size of an electron, or the size of a shell, or the size of an atom in simple form. Like I said, it tells how the size will be. As we see that it will be always increasing. If L, for example, if it has 2 shells, N1 it will be L0, then N2 it will be L0, L1. So it's something which is always increasing, which determines the size of something. So that's under nombre quantique secondaire. The nombre quantique magnetic, we have known the stage, we have known the flat, which is the shell, we have known the stage, which is the subshell. Now we're going to look now into the apartment, which is the nombre quantique magnetic, in how are these electrons arranged, the orientation of these electrons. So we have to know the orientation of these electrons. So, nombre quantique magnétique, il indiquait le nombre d'orbiteurs correspondant à une couche énergétique donnée. So, this one corresponds to orbital numbers, like it corresponds to, I can say, you know how, you know its arrangement, and you know how many orbitals it makes, and how many, how many orbitals or how many turnings does it make. You know all that in this apartment. You know its orbital number, you know its orientation, how this electron is arranged. And yeah, I know this is something which is very complex in such a way that you are thinking, how can you a shell for, like, even me when I was coming from Zambia, I had this view of a shell where I would just find an electron there and then, but they introduce something new in such a way that you have to start from a flat, you have to go to a stage with subshell, and for you to find an electron, actually you have to go through stages. These are the stages which I'm telling you, and don't, it's something which is very simple. Don't get confused, and yeah, with time you actually understand this. So M est la projection de different orientation du moment sur la direction du champ magnétique. So we see that M is the projection of different orientation. So M actually is the projection of how an electron is oriented. So for you to find the orientation of an electron, you have to consider that negative L must be less or equal to M, and must be less or equal to what? L. So you should know that the M, if they have given you your L, if you know your L, you can, so for you to calculate its orbital and how this electron is moving, you have to know its L. So if they have given you your L must start from a negative going towards 0 and to a positive, the same number. For example, I'll give you an example, don't worry. The example, so for example, we have got n is equal to 2, where L is equal to 0, 1. Since if n is equal to 2, if you use that formula n minus 1, you said L always starts from 0, so L is equal to 0, then n minus 1 is equal to 1. Just the same where L is equal to 0, L is equal to 1. So don't get confused here. So we see that first we write for L is equal to 0, then we find this nombre quantique magnitude. So how do you find this nombre quantique magnitude? If L is equal to 0, correspond to M, its magnitude, since you are saying you have to start the formula, you have to start from a negative, going to M, going to positive. This is a positive number. So if L is equal to 0, meaning 0 is neither negative or a positive number. So meaning the orbital M is equal to 0, which if M is equal to 0, meaning there's only one orbital. I don't know if you understand this. There's only one orbital, meaning this is the electron has only one orbital. It's just moving in a what? One orbital. So yeah, so you have to research on this. When I say orbital, basically this is what I mean, like something which is moving in its orbital, like the way it's arranged. Like the way it's arranged is, you cannot find a different arrangement. When I say orbital here, I mean the way it's arranged, you can't find its different arrangement. You only find the one arrangement which is in the form of a circle. So this arrangement is just one. When M is equal to 0, this arrangement is just one. But when you go to L is equal to 1, L is equal to 1. So we've done for L is equal to 0. Then L is equal to 1. We have M is equal to negative 1, 0, and 1. Since I said we begin from negative, going towards the positive. So when it is 1, you begin from negative 1, going to. So this one has what? 3 orbitals, meaning it can be arranged in 3 forms. It can be arranged either in the X form, can be arranged in the Z form, or it can be arranged in the what? Y form. So it can be arranged in the what? 3 forms. So basically the orbital, when I say one orbital, means I can only arrange, there's no other way how I can arrange this. I can only arrange it in one form. Then if I say 3 orbital, meaning it's possible if I find this orbital, meaning in this apartment, which I am, this electron can be found in 3 different positions or 3 different arrangements. Yeah, someone else you can ask your question.
Yeah, thank you. These guys like SPDF, are they those, yeah, the orbitals like those on hybridization, are they related somehow? Like,
What? I can't get your question. You can rephrase it. You can ask it again. I didn't get it. Question.
okay, here on SPDF, I think I didn't understand well here. Are these guys, oh, are these SPDF related to hybridization, those orbitals on hybridization?
You are saying these are related to the last part. I'm not getting your last part. I don't know the network.
Oh yeah, these are the SPDF. Are they orbitals or what?
Oh yeah, I get you now. SPDF. They are. I can say they are not orbitals. They are. I can say they are subshells where you can find they are not actually as orbital. They are not orbitals. They are subshells where you can find electrons. For example, generally, I can say I'll give you an example of an egg. You see, an egg has an outer part, which you say a shell. This is the N, which you have principal what? Principal, which we say principal quantic principal N. Then it has this, the outer part, it has got the outer part of a shell. It has got the inner part, which is I can say that the covering, like something which is white. When you're opening an egg, there's something which we remove with the shell, the whiter part. The whiter part, that's we can call a subshell. So basically, there's a covering which is a shell. Then a subshell is where you find the electrons. Like for example, when I say on this one, getting clearly, when I say there's a covering, which is a shell, then there's a subshell where I find electrons. For example, the Zambian one, if you remember the Zambian one, you see that this subshell is the one where you find where it has a fixed number of, like, if the first shell, the first shell must occupy 2 electrons. So where the maximum, so S has a maximum in such a way that S must only occupy 2 electrons. Then P has a maximum when you go to the next shell, which must occupy, for example, in Zambia, we said the first one must occupy 2 electrons, then it's full. The second one must occupy 8 electrons, then it's full. The third one must occupy 18 electrons, then it's full. That's how the subshells is. Just it just tells us the size and how electrons must be occupied. So the S, actually, this S, when I say S, the S is to represent that in this S, in this shell, in this subshell, S is maximum, like the maximum of electrons which S must occupy. That's why it's always 2. Then in P, the maximum of electrons which it should occupy is always 6. Then in D, the maximum electrons which it should occupy is 10. It's like you're moving from different shell, how you arrange the electrons. Then in F, the maximum electron which should occupy is 14. So each, if you see the trend is S2, I add 4, P6, I add 4, P10, I add D10, I add 4, F10. So it's just the how you can put the electrons. Like it tells you you can't exceed this. You can't exceed this when you're arranging the electrons. And the non-quantic magnetic, it tells us the actual orientation, how the electron are arranged. Is it how are they arranged actually in an orbit, or in how many forms can you arrange them? So the magnetic quantic magnetic, it just tells us in how many forms can you arrange them. Is it one form or two form or the third or three forms, or yeah? So magnetic quantic, it tells us the form and how you can arrange it. I don't know if it's clear.
Yeah, it's clear. Thank you.
Yeah, so that's also this one, like when you come for under electron configuration.
A question.
Yeah,
Can you also say these are energy levels?
yeah, they correspond to energy levels.
All right.
Yeah, they correspond to energy levels in such a way that, but you should always bear in mind that at each point you go to another shell, you always start on S when you are writing configuration. What I mean is, for example, I'll give which example can I give? I can give helium, which has a proton number 4. Helium has a proton number 4. So the first shell, it will occupy, I'll write, when I'm writing configuration, it will be, I always, if it is the first shell, I indicate it by 1 when starting 1. Then that first shell, there's S. Then I write 1. I'll write 1. Then after that, I'll write S. Then S must occupy 2 electrons. Then when I go to another shell, I'll write 2, the another subshell, I'll write 2, S, and that subshell must, since there is 4, must occupy 2 also. So as you go to another subshell, you yeah, so those things are things which we'll learn about, and there are things which are, I can say it corresponds to the energy levels, as you said. Yeah. So, and the non-quantic magnetic just tells us in how many forms can you arrange it. So, if, for example, if there's one orbital, meaning I can only arrange it in one orbital. I can only arrange it in one form, like as I showed you earlier here, it can only arrange, there's Z, Y, X, but it can only arrange in one form. But if my L is equal to 1, meaning I can arrange it, there's -1, 0, 1. So since according to our equation, it's starting from -L, less or equal to M, less or equal to L. So it's -1, 0, 1. So I'm going to the positive. So there are 3 orbitals, meaning when I write 3 orbitals, meaning I can arrange it, or I can orient it in 3 forms, which is, if you see here, it can be either in a X, Y, either in a X, Z, or Y form. Then if you continue, but for you guys, for you guys, like we just switch here. We don't go deep until this part down here, the arrangement, that how they arranged here when N is go, maybe when N is equal to 6, 7, you don't go beyond that. Yeah, you're only limited here. That's where we are all limited. When you see most of the things, when you do your work, they don't go beyond, because it's very complicated. Like it's very complex and it's very difficult. We do that. We do diagram, molecule diagram, and you will see how they orient, how they put it, and how they do all these things. Yeah. So after that, so we have seen the shell, the subshell, where how electrons are arranged, then the quantity magnetic, which is the apartment, in what forms, or what form can they be arranged? What forms is it? In one form or three forms? It depends with your L. So your L is your quantity, nombre quantique secondaire is the one which tells us everything, yeah, of how we should arrange it. So this diagram simply, it tells us this is, for example, if L, this is for L is 0, which represent S. This is, I can say, if L is if L is 0, which represent S, then in S there's always what? One, I can say there's always one orbital. In one, if you see in one, there's always what? 3 orbital. One represent P, the subshell P, the second subshell. Then 2, it represents the third subshell D, which is there are 5. So it always increases. So 2, it will be -2, -1, 0, 1, 2. It should be -2, 1, -2, 2, 0, 3, 1, 4, 2, 5. So it's arranged in what? In 5 different forms, which is this one here. If you see, it is 1, 2, 3, 4, 5. So it's arranged in 5 different forms, which is very complex. It's very complex, and you can't go beyond L is equal to what? To most of the times they don't usually go beyond. If you go beyond in under molecular what, is very difficult for you to calculate the molecular for you to draw the molecular diagram. So they don't usually go beyond 2. Then if it's 3, it represents F, and this what will be 7 in such a way that it will be -3, -2, -1, 0, 1, 2, 3. Then when you count all those, it will give you this orbital, which will be 7. So basically, that's how you find. They will ask you questions. How can you find the orbital of n is equal to 2? First, you divide it. Like first one, it will be L is equal to 0. Then the second one, you continue. You continue like when you're finding L is n minus 1. You say, for example, if n is equal to 3, the first one is L is equal to 0. Then the second one, 3 minus 1, it will give you L is equal to 2. Then you go down, 2 minus 1 to give you L is equal to what? To 1. So until you do all that, then you know that in this shell there's this orbital. In that shell is this in that nombre secondary L, there's this orbital. In that nombre secondary L, which is equal to 1, there's that orbital. Then when you add all those orbitals, you find the orbital, the shell in general. So those are things which are like, there are things which are very simple. Most of the time, the questions, they'll just ask you, what does in what orbit does N2 find this orbital, find the orbital of n is equal to 2. You have to know how to calculate your L first, then you have to know how to find your M, your number magnetic. Then you are good. Then so if you have this idea of how you calculate, most of the times what comes is calculation. They don't explanation is not really that much, but calculations are things which come. So you have to know how to calculate, and you have to understand these things. Yeah, I don't know if until there is clear. If there are any questions, you can ask. It's better to ask questions and you are moving, you are not, if you haven't understood.
I think it's clear.
Okay, so yeah, so now we'll continue. So we'll look at the last one, which is nombre quantique de spin. This one now, it tells us the other position of an electron where you can actually find an electron, where you can like, this one tells us the room in which you can find an electron. So the first one, quantique, it was the flat itself. Then secondary air was the stage. Then magnitude, magnetic, it was the apartment. Then the spin, it tells us the room in which you can find this electron, and how much or how many should this room occupy. So what you should know that MS correspond à la quantification du moment cinétique de l'électron tourné sur lui-même. So nombre quantique de spin, which is denoted as MS, it corresponds to the quantification of a moment, kinetic moment, like movement of an electron, to which is moving around itself. So you know its room, and for you to know when you go in each room, what you should know always that each room, like when you go in each room, it must always occupy 2 electrons, which each room occupies 2 electrons which are identical. 2 electrons which are identical, and these electrons, they spin different. So for you to know to differentiate them, the other one will be spinning the clockwise direction, which is this one, the positive here, and the other one will be spinning the anti-clockwise direction. So according to how they are spinning, you know the electron which you are looking for. So after you have known the apartment, you have got into a room, and the room you have seen that there are 2 electrons, and you are looking for an electron which has a spin meaning it is moving. It is creating a momentum in such a way that it's circulating on its axis. You know, when I say it's circulating on its axis, I mean that it's not actually circulating as in it's not actually circulating around, but it's moving like it's moving. When it's moving around, it's also moving in this axis, like this. There's an axis which is created, like here. When you see here, there's an axis which is created and which is making an electron to move. This is a clockwise direction. This is anti-clockwise direction, and its movement always is always not complete. It's half always. It moves half. So there will be half movement and the half movement anti-clockwise. So there will be half movement the clockwise direction, and the half movement the anti-clockwise direction. So that's how you know the electron. So first of all, you have to know its number quantique, which is n. After you know its number quantique, which is the flat, you have to know its number quantique secondaire, which is L. After you have known its number quantique secondaire, which is L, how the electrons are arranged in a subshells S, P, D, F. After you have known, then you have to know in which form is these electrons arranged. Is it in a form? Is it only one form or different forms? Is it only one form or different forms on which I can find these electrons, like their forms? You see that according to the N, you know how these forms are, how they are arranged, if it is 3 forms or if it is only one form. Then after that, you arrange, you see the orientation, you know the orientation, you go to their room and you check, is it, am I looking for the one which is moving clockwise or the one which is moving anti-clockwise? Then you say, I'm looking for the one which is moving clockwise. Then you get the one which has the arrow which is pointing up, is the one which is moving clockwise, and you will find its position. So basically, it was all about finding a position of an electron. So most of the times they tell you like to write they say it cut what yeah, to write the cut of an atom. When they say a cut, they basically mean you show it in terms of arrows. Yeah, you show it in terms of arrows. I don't know if I have something down here. Let me check for you. In terms of how they are spinning. Yeah, I think I have something. Yeah, this is how you write it in a cut form in terms of how what that's meaning. So when I say each room occupies 2, meaning this room can only occupy the up and the down. It can never occupy more than 2. So the first thing is, according to you feel according to the number of you feel according to if you are given an atom, first you write this configuration, and when you write this configuration, you know that after writing this configuration, if you are given a number, yeah. So here I want you to follow me. So when you're given a number, let me say you say n is equal to 4. For helium, we say 1s squared. That's I'm saying this configuration. 1s squared, 2s squared. Yeah, you have written 1s squared, 2s squared. No, let's get since that one is something which is stable. Let's get boron, for example. Boron, yeah, boron is n is equal to 5. I think so. Let's get for n is equal to 5. You have, when you're writing, each atomic number is equal to 5. When you're writing it, you have 1s2, 2s2, then 2p. The electron which is remaining is 1. Since 1s2 is 2 electrons, you have already written 2s2, 4 electrons, then 2p, 1 to give you, when you add those electrons together, to give you 5. So how do you arrange them? So when you're arranging them, the S part, when you're arranging them, the S part, according to the diagram here, the S part only has 1 room. I said this is, yeah, the S part only has 1 room. When you go to the rooms, it only has 1 room, and this room must only occupy 2 electrons. So the S shell only occupies 2 electrons. So that's why I said the maximum of S is 2. So it will be 1s2. Yeah, it can occupy 2 or less than 2. Then the maximum of P has got 3. It means it has got what? 3 rooms. And we say that each room must occupy what? 2 electrons. So meaning if there are 3 rooms, if there are 3 rooms, the first room will occupy 2 electrons, the second room will occupy 2 electrons, and the third room must occupy what? 2 electrons. So which means altogether, for it to be stable, if you 3 times 2 is what? Is 6. So in all, the electrons must be 6. Then for the fourth room, for D, it has got 5 rooms, and each room must occupy what? 2 electrons. According to the spin which we have done, the spin, it tells us that each room must occupy what? 2 electrons, which will have 10. If it is 5, you have just multiply 5 times 10. That's why we're saying for a D shell to be full, it has to have 10 electrons. Yeah, it has to have 10 electrons, and this is basically represented in a form of, you can represent it in a form of arrows, the one which I was telling you about, the one which I was talking about, the arrows, the up, the down, the up, the down. So this one, you have seen this one, there's 3 rooms, 1, 2, 3. Then you have known that it comes from what? P. If you have 3 rooms, it comes from P, and P, basically in P, it was like, for example, it was 2P, I can say it was 2P5. For example, let's assume it was 2P5. In P, there were what? There are 5 electrons. So what you do first, when you are putting these electrons in their rooms, you first put the upward, the upward, the upward. Then after putting the upward, then that's when you put the downward. You put the upward, then the downward, the upward. No, you will leave the you find that the last part it will be empty. So the first you start with the upward first. Then after upward first you are done with the upward. You can start the downward according to the number of electrons which you have. So P can carry from 6 going less, 6 less. 6 is the maximum. So when it carries, so this, like for this one, the P is not stable because it's not full. For it to be full, it must have, the room must have 2. So you see for this one is stable, this one is only has 1, this one has 1. So something like the P in general is not what? It's not stable. So according to the subshells, you know the room which should always know that S occupies 1 room. For S, it occupies 1 room. For P, it occupies 3 rooms. For D, it occupies 5 rooms. For F, we continue. So what determines the rooms is when you know the orbital. So these things actually they are linked. So for you to know the room, for you after you have found your configuration, after you have written your configuration, because each one for S you write, for S again you write, and for P you write. For example, the one which have for boron we have 1s2, 2s2, 2p, 1. So 1s2, I'll write 1 room for S, which I'll present since there are 2 electrons already. I'll present 2. Then 2s2, 2s to the power 2. I'll write a room since S present 1 room. Then I'll present those 2 electrons. Then 2p1, I'll write 3 rooms. Then since P there's only 1 electron, I'll only present the upward arrow, only 1 upward arrow in first room. Then these others will be what? Empty. Then I've written my cut. The cut, they call it cut. They call it a cut. They will write the cut for this one. This one simply a cut. And the electron configuration, those things are basically like they're simple. The electron configuration thing. So this is what you should always know. So this basically it just brings us to how you can write a configuration and how you can know how you can know the maximum number of electrons which each subshell must have. So if you know your n is equal to 1, you know how to calculate your L. We said L is equal to n minus 1, and you know how to calculate your magnitude, where m is equal to negative L to positive L. You know your orbital. You know how to arrange them in a room. How to arrange them, and you should always have this principle in mind that each room always occupies 2, which is the upward and the downward. Then when you these things, if you do a lot of questions, that's when you can understand. You understand it clearly. Yeah, I'll see if there are some questions which I can look for you guys. Then I'll give you those questions, and you try doing the questions. That's when you do. So basically, you just have to know how to calculate, how to come up with the orbital, all those things. So yeah, so different types of orbital. Souvent, la value de R, on distinguit different types d'orbital. Le nombre de values de M correspondait à une value donnée de R. So for R is equal to 0. So we say most of the times for values of R, we distinguish different types of orbital. As we said, like if R is equal to 0, we have only 1 orbital. If R is equal to 1, we have negative 1, 0, 1. We have 3 orbitals. So that's how we distinguish the orbitals, how they are arranged. So the number de values de M correspondait à une value donnée de R. So you have to know your nombre quantique secondaire for you to find the nombre magnetic. So if R is equal to 0, it means the orbital is under the shell S. if L is equal to 0, which I said, and it's only one room, and this one room, it occupies two electrons, which is one is up, the other one is down. Then when L is equal to 1, you have -1, 0, 1. You have orbital P, which has 3 rooms, -1, 0, 1. So these orbitals, they give you rooms, and this room each room must occupy electron for it to be full. But it depends with your P. If your P has 5 electrons in the shell, it means it will only show 5 electrons in such a way that you first put the upward electrons. That's when you start filling. Then when L is equal to 2, you have -2, -1, 0, 1, 2. It means it will be 5. Yeah, it means your orbital is 5, and your rooms will be 5, and each room will occupy 2 electrons. So that's how it is. For L is equal to 3, the same thing. You go -3, -2, then you know how each room, how many electrons, what is the maximum when you are writing your configuration. So if you put this in mind, you will know that the S is 2, the P is 6, the maximum 2 or less. So the S is 2, it can occupy 2 or less. The P can occupy 6 or less. The D can occupy 10 or less. The F can occupy 40 or less electrons. That's what you should know, basically. Yeah, so those are the orientation which I was talking about. Yeah, everything. So this is the drawing which I was talking about. This one is very important. This one, when in S is always, when there's one orbital, can be presented in one orientation, but when there are 3 orbitals, it can be represented in what? 3 forms. These are the forms which I was talking about, basically. Yeah. So for today, we'll end here since we don't have time. I don't know if there are any questions before we close. Then I'll ask you on Sunday so that we do slatters, and I'll just show you how to write the electron configuration, yeah, slatters, and also how to write the diagrams of molecule orbital. Then if you know those things, those are the things which usually come on exam. You'll be assured of getting between 15 and 20. If you know those things, if you have those things, you'll be sure to get between 15 and 20. So I don't know if there is any question until there, so that I can explain. Oh, okay. For time, I'll communicate to you guys. Like for time, I'll communicate to you. I'll tell you the time. Yeah, since I don't know, some of you go to church, but I was thinking 14 hours. I don't know if it's 14 hours. You'll be back. It's better. Yeah, I don't know on your views. So I was thinking 14 hours. Yeah, Kenneth, you want to say something?
What of maybe 15 or 16, because the church services, they don't usually end exactly at 14. Sometimes they end at 14:10, 14:15, and at least some time to rest before the lesson would be good.
Okay. I don't know if everyone seconds that. So 16, 15. So yeah, for me it's just okay.
Yeah, I think 16 will be the best time.
So yeah, so 16. I'll prepare something for you guys, and yeah, we'll be doing the configuration. We'll just do the configuration, how to do with the configuration, and how to write a molecule, all those things. Yeah. So 16. That's when we'll meet, and I'll communicate with you. Yeah, I'll communicate with you in the group. Then I also sent, there's a question under incertitude. I'll send the question. Yeah, just check just the same formulas. It's not something which is very difficult. Yeah. Okay, have a nice day, and yeah, enjoy your day.